make sure you go to this joinpd.com and enter the code EKDLKB. And that's important because you have to enter your answers there. Every question that I put out, you have to enter the answers there. Just hold on 1 minute. This is a call I might have to take. Let's take this. Apologies for that. I think something I was hoping to avoid, but couldn't avoid it. Just hold on 1 minute. So hopefully enough people are there on the join PD session. So let's go on to the first problem, which will come up right now. So these questions are basically on Markov inequality and very basic questions to begin with. And we will go forward and make it more complicated as it goes along. Okay, so let's get started. I'll give you only a couple of minutes for this. This is a very quick question. Okay. Okay, so I see a few responses already. So suppose, I hope the question is clear. There is 100 students in the class and 50 is the average in an exam. So you're supposed to look at this one. So let me just also set up one more thing. Okay. So I see about 8 responses. We wait for at least 10 or 15 or so and then show you. So it's sort of a basis for the Markov inequality, like asking this simple question. I also talk about such things in the lecture, I think. Okay, so there are about 15 answers. So let's see how the answers is. 55.55, 0.955. I think 55, why do you say 0.55? 0.55 cannot be the number of people, right? So there's got to be some multiplication by 100, right? 55, 5 by 9 times what? 100. Okay, so 55 is the correct answer. So how can one argue this one? So in case you want to argue this, you can do this. So you can take a look at this one. So you can use Markov inequality and all that, but let me just show you something very simple here. So if 100 students have written an exam and the average marks is 50, what is the total marks? The total marks has to be 5,000, isn't it? When you add up all the marks of the students, you should get 5,000. That 5,000 was divided by 100 to get 50, right? So if people have to get more than 90, what is the maximum number of people who would have to get 90? You have to divide the 5,000 by 90, right? Supposing everybody got 90, right? That would be the maximum number of people getting 90, and the total has to be 5,000. So it needs to be like 55, 56 types, right? So around 55, getting 90 can give you a total of 5,000. So that's, it cannot be more than that. Supposing, I mean, clearly it cannot be that all the 100 got 90, right? If all the 100 got 90, then the total is 9,000. Okay, only about, since because the average is 50, you cannot have very large marks for a lot of people. Okay, so this is sort of the basis for the Markov inequality intuitively, but you can use the inequality more rigorously to get exact numbers. So this 55 comes from that. You can just divide 5,000 by 90. Okay, so that's the idea. Hopefully that's clear enough. Let's move on to the next problem, which is a more, yeah. So if you go to the worst case where, so the situation that Ashwin is pointing out is, you can have an extreme situation where all 100 got 90. No, not all 100. 55 got 90, and then remaining 45 got 0. Even then, the average will be 50, right? So the average being 50 corresponds to that worst case in some sense of 55 people getting 90. Even in that case, only 55 will get, not more than 55 can get 90. Okay, so that's the story there. Let's move on to the next one. So this is a very textbook application of Markov inequality. Markov inequality, as you know, is probability that x is greater than some number, I don't know, you can use anything you like there, k, that is less than or equal to expected value of x divided by k. Okay, so here I'm given a continuous random variable which is uniformly distributed in 0, 10. Okay, and you have to find an upper bound on probability that x is greater than 8 using Markov inequality. So now here again, you may want to use some simple facts about continuous random variables. For that, I had asked for something. Let me just check on this. Oh, doesn't work. Okay. Okay, so I was just trying to get to some screen. So let me hold on 1 minute. I'll just stop sharing for a minute and then come back to you. Uh, just trying to pull up one document that I have, which has a table of distributions, which I think might be useful for you. Okay, so let me share the screen once again. Hold on 1 minute. So I got instructors were kind enough to do this little table here for you. So hopefully you can see it. So if you have uniform between A, B, the PDF is this, the CDF is this, the expected value is just A plus B by 2. Okay. So I was trying to show you that it's just A plus B by 2. So that's an easy enough thing for you to see. So I was trying to get to the screen. So let's go back to the screen. Let me see how many people have answered. So the expected value, the first step is to find the expected value of this distribution. Once you find this Markov inequality, is just straightforward to use, right? Probability that x is greater than something is less than or equal to expected value of x by that same thing. So once you find the expected value, the answer will be clear. So the actual probability, how do you find the actual probability? So it's probability that x is greater than 8. So you have to find the area under this PDF for greater than 8. Okay. All right. So let's see the responses. Quite a few people have responded. 5 by 8 and 1 by 5. Okay. So I think many people have got it right. 0.625. They've not entered the next one. Actual probability is 1 by 5. Okay, good. So 5 by 8 is the upper bound. Actual probability is 1 by 5. So that's correct. A lot of people have got 0.625. Some people have got 0.5125. 5.625. What happened? 0.25. Okay. Okay. So looks like people have got roughly to the answer. So let me now take this time to go back to the solutions for both the questions. Okay. So here is the solution to both the questions. So let's start with the second one, part B. This is the more textbook variety. So if you look at the uniform distribution from 0 to 10, here is a picture of the PDF. You can see from 0 to 10, it's flat and the height is 1 by 10. Okay, so this is a picture of the PDF. So if you want to find the actual probability that x is greater than 10, you have to find the area to the right of 10, right? X is greater than 8. Okay, so this area. So that area is just, 1 by 10. So 1 by 10 is the height and the width is 10 minus 8, that's 2, right? So it's 2 into 1 by 10, so that's 1 by 5, so it's 0.2. Okay, so 0.2 is the actual probability. Notice what Markov inequality is giving you. X is greater than 8 is less than or equal to expected value of x by 8, 5 by 8, 0.625. It seems far off, and that's generally usually true for Markov inequality.
Sir,
Okay, so you got
can I
a
ask a
feedback.
question, sir?
You can type the question on the chat window. I'll take a look at it. I think that's best. Okay.
Okay. Okay.
I will take a look at questions in the chat window. Please type it in the chat window if you have any question. Okay, so let's move on to the next question. It's again a slightly different application of Markov inequality, but again straightforward. I'm not expecting too much trouble here with this one. It's a fair coin. Okay, so what is the question in the chat? I'm sorry. So, okay, wait. I mean, this question is a bit confusing to me. I've asked for the upper bound for the probability. So I've asked for an upper bound for the probability. Why do you say 5 plus? No. I think you're getting a little confused here. So you're adding 5 because 5 is the expected value of x, is it? No. That's not. No. That's not how Markov inequality works, right? Markov inequality is just probability that x is greater than some number is less than or equal to expected value of x by that number. That's all. There's nothing like adding 5 to it because I've asked for an upper bound. I just don't quite get it. I think it's just Markov inequality is probability that x is greater than anything is less than or equal to expected value of x divided by that same thing. That's all. That's Markov inequality. So if I want an upper bound on the probability that x is greater than 8, it is just 5 by 8. And anyway, it's an upper bound on the probability of something. What's the point of saying 5.625? I mean, anyway, upper bound is 1, right? Probability can only be between 0 and 1. There's no question of adding 5 to it. Okay? There's no, I think there's maybe some confusion which I'm not able to understand where it comes from. So think about that. You can go back and look at how the Markov inequality is defined. See this. So here's another question. Here again, instead of giving you the random variable directly, I've given a situation where there is some random variable for which we're trying to find some probability upper bound. Okay. So you have to sort of identify the random variable of interest here. Okay. The random variable of interest here is number of heads seen when a fair coin is tossed 200 times. Okay. You know that that random variable has a binomial distribution, and then you can find its expected value of x. Once you find expected value of x, it's a question of Markov inequality again, right? Probability that x is greater than 150 is what I'm finding. So it will be less than or equal to that expected value you found divided by 150. Okay, that's the upper bound. The upper bound is expected value of x divided by that value, probability that x is greater than t is less than or equal to expected value of x divided by t. Okay, so that's the value. Okay, so I have about 21 responses. Okay, once again, the random variable in question here is number of heads when a fair coin is tossed 200 times. And then you can do, and then the question that's being asked is probability that x is greater than 150. Okay, it will be less than or equal to expected value of x divided by 150. What is expected value of x? When a fair coin is tossed 200 times, what is expected number of heads? So once you calculate that, you're done. Yeah, so there is an answer that's coming out. 100, it's about roughly half the people have responded. So let me just see. Yeah, 2 by 3.67. It's not 1 by 3. Some people have said 1 by 3. That's wrong. So it's 2 by 3. Okay, how do you get 1 by 3? I don't know. So 1 by 3 must be some simple mistake here. The answer is 2 by 3. That's correct. Okay, so answer is 2 by 3. Its expected value of x is 100. So it's just 100 by 150. Okay, so let's move on to the next one. Again, a binomial, small, very small variation. There's nothing more to it. So there's a question on chat. Let me go take a look at it. Yeah, so Anupam is asking a question that it can turn out that the Markov inequality will give this ridiculous answer that the upper bound is greater than 1. In that case, you can simply say it's less than 1, right? So one of the ways in which Markov inequality is used is you'd say probability that x is greater than t is less than or equal to expected value of x given divided by t or 1, whichever is smaller, right? You can state it like that. Yeah. So the upper bound is strictly valid, right? 100 by 90 is definitely an upper bound on the probability, but it's just a comical upper bound. You can just say 1. So Markov inequality can be poor. That's the answer. Okay. Hopefully that answers Anupam's question. Anushka Singh has asked another question. What will be probability that x equals 150? So that's just a binomial calculation, right? It will be 200 choose 150, p power 150, 1 minus p power 50. Okay, so you can write all that down. You can calculate, that'll be the answer. Okay, so it will be some big quantity, it's difficult to calculate. So the utility of Markov inequality is that, all that if you add, you will get, something like it's just smaller than 2 by 3. Okay, if you add up everything from 151 onwards, you will get 50. So to enter your answer, please go to joinpd.com and enter the code EKDLKB and enter all your answers there. Don't put your answers on the chat box. Chat box is for asking doubts. Okay. Joinpd.com and the code is on the top right, EKDLKB. Okay, so let me see. It's again a straightforward sort of question. Simple application of Markov inequality. The answer is 4 by 9, 2 by 9, 0.44, 4 by 9, 2 by 9. Some people are saying 2 by 9. Many people are saying 4 by 9. Looks like 4 by 9 is likely to be the correct answer. Remember, it's tossed 200 times. Maybe you thought it's tossed 100 times. I don't know. It's tossed 200 times. So let me see. I think I've written up some solutions for the question 2 also. Let's go to that. Okay. So straightforward once again. So x is number of heads in binomial 200 comma half in the first part. So expected value of x is 200 into half, which is 100. and then probability that x is greater than 150 is just less than this. So in the second case, it's a biased coin. So it's x is binomial 200 comma 1 by 3. Remember that 1 by 3 is important. So expected value of x is 200 into 1 by 3. So it's 200 by 3. And then you again do the same calculation, you will get a 4 by 9. So if you just took blindly this 100 as the expected value from last time, you'll go wrong because this is 1 by 3. Okay, good. So that's done. Yes, yes. So the question from Samit is exactly right. So Markov, Chebyshev, Chernoff, they're all bounds for the probability of an event. Okay, what is that event? Random variable is greater than something usually. Okay, or in the Chebyshev case, it's absolute value of x minus expected value of x is greater than something. In the Chernoff case also, it can be something like that. But yeah, it's usually you can think of it as upper bounds for what are called tail probabilities. Probability that the x is taking values too far away from the expected value. Okay. So yeah, so the three of them could be called Russian mafia if you're particularly afraid of these inequalities. This is a straightforward application. So I hope you appreciate this inequality. See, if you have to find the actual value of this probability, you have to add up a lot of binomial terms. Of course, today's computers may give you an answer very quickly, but there were days when there were no computers. So how do you get a sense of how big that value is? So this kind of inequalities come to help you. Okay. So I'll show you more cases which are interesting as we go along. Okay, so now we move on to continuous distributions. So here is a exponential distribution. So let me just show you very quick how the exponential distribution looks. So this is the exponential distribution. For exponential lambda, the PDF is lambda e power minus lambda x, and x is positive. And the mean is 1 by lambda. Variance is 1 by lambda squared. So that's a formula for you. A lot of you are complaining about the number of formulas you have to remember. So here is a table to help you. Okay. So this is the question. Okay, so x is exponential 4. Hopefully you saw from the formula. Yes, yes, yes. That similar table will be available in the exam. No problem. Okay. So find an upper bound on probability that x is greater than 4. Okay. So exponential 4, the expected value is 1 by 4. So expected value is 1 by 4, and here we're asking probability that x is greater than 4. So it's sort of significantly far away from the mean. So you expect a reasonable answer from Markov. Okay, people have quickly come to the answer. So let me show you the responses. 1 by 16. Okay. So why do you thank God? You have to thank the teacher, right? No? Don't you want to thank the instructors and the faculty? No? Seems like the wrong direction in which your thanks is going. Okay. So there was also a question on the actual probability, and some of you have actually found the probability, some of you have not. So the probability will okay. Uh, okay, so some request to the studio team. I don't know if okay, so this question on upper bound, same as supremum. Think so. Supremum is usually for a set. I'm thinking of upper bound differently. Let's not go there. Let's finish this one. The actual probability, you need to do an integration, or remember, this is probability that x is greater than 4. You can even use the CDF, right? The CDF of the exponential distribution, and do the calculation. You remember the CDF, right? The CDF is given here. The CDF of exponential is 1 minus e power minus lambda x for x greater than 0. Okay, so that's the CDF. So CDF is what? What is it? It's a probability of the event that the exponential lambda random variable is less than or equal to small x. That's the CDF. Now, what's asked here is the probability that x is greater than 4. So it will be what? 1 minus the CDF, right? Evaluated at 4. So you can even evaluate the actual probability. It's not too difficult for the something. Okay. Actual probability. Okay. So for these kind of cases, so Samit is right when he says for these kind of textbook cases, when the distribution is well known, using Markov is just an exercise for you. At this time, I'm getting you used to the application of Markov. We will see later on situations where the distribution may not be known. So or it's too cumbersome to find out. We'll come to it. You're only in the third problem. As we go along, you will quickly come to a situation where finding the actual distribution is majorly difficult. It's not even possible to find out some cases. There, Markov will give you a bound. Okay, so we will come to it. I mean, right now you're right. I mean, in these cases you can find the actual probability. So why do you need Markov? You don't need Markov. Okay. Okay, so quite a few people have found Markov. They are too lazy to find the actual probability, except for one person who has actually found it. Is it 4 e power minus 16 or just e power minus 16? I don't think the 4 will come. I think integration is a bit tricky here. I don't think the 4 will come. Anyway, let's go to part B in question 3. Okay, so part of my reason why I'm giving this example is to actually show you the Markov inequality can give you answers which are far away from the actual answers. Okay, so knowing the distribution is a huge thing. It's a big power if you know the distribution. But most cases you're just given data, right? I mean, you have to sort of guess at the distribution, so it's not so easy. One can use Chernoff also. You'll see. I mean, I'll come to it. I'll show you some examples where even Chernoff is tough, right? What do you need for Chernoff? For Markov, you just need expected value. For Chebyshev, you already need variance. You'll see, can be very difficult to find in some situations. And for Chernoff, you need what? You need a bound on the moment generating function. And where will you go for all that? I mean, it depends on the problem. For easy problems, yes, you can do everything. You can find the actual thing. But places where these are used, it's very difficult to find the distribution. It may be very difficult to find the variance. Definitely, it may be impossible to find the moment generating function. So those kind of cases, you'll see. You'll see it. It'll come. Okay. So this is Poisson. Poisson, once again, I mean, if you forgot the formula, let me just come back and show you the formula here. Poisson distribution is right there. Poisson lambda. Mean is lambda. Variance is also lambda. Okay, mean and variance both are lambda for the Poisson distribution. So you can use right here that for Poisson 4, mean is 4. So expected value of x is 4. If you use Markov inequality, you're going to get a really, really simple bound. 1 by 3 is absolutely right. 1 by 48. You get 48. Okay. See, remember for Poisson, I think, okay, now comes the confusion. For Poisson lambda, mean is lambda. It's not 1 by lambda. Okay. I know it's confusing for many people. A lot of people have taken 1 by lambda here. That's why you got 1 by 48. It's only lambda. Okay. So be careful about that. Poisson is lambda. Exponential is 1 by lambda. Okay, so anyway, we'll give you the formula sheet. I mean, I'm not able to share two screens at the same time. So you'll see the formula sheet and hopefully you won't make these kind of mistakes. Okay, good. 1 by 3 is the correct answer. Next, the final thing is geometric. Again, a case where the actual probability is known and you can compute. It's just for you to get used to the idea of how to compute these things. The geometric distribution, once again, if you want to see the formula, geometric P is mean is 1 by P. Okay, variance is 1 minus P by P squared. Mean is 1 by P. Okay, so geometric distribution mean will be 4, right? Because it's 1 by 4. So mean is going to be 4. It should be relatively easy to find the sum. Okay, so first three problems are just textbook applications, just for you to repeatedly do these calculations so that you remember what the Markov inequality is. Okay, so that you won't forget even Somebody in the middle of the night wakes you up and asks for Markov, you should immediately say what the answer is, right? So for that kind of purpose, you do 3 questions. So that's good. So can you please add the table of formulae to our lecture notes? Okay. Your lecture notes, meaning what? I mean, in the portal, you mean? Okay, so we can have that in the portal, add it in the portal. It'll be part of your exams also. And anyway, I mean, you search for the distribution on Wiki. Wiki has a very clean description of the entire everything. So, but yeah, we will add it to the portal for sure. Okay. Okay. 1 by 32. Oh, okay. So I think again the confusion is geometric P, the mean is 1 by P. So it's 1 by 1 by 4. So the mean becomes 4. Okay. So be careful about these kind of things. Okay. 1 by 32 is not the correct answer. Yeah, so that's true. I think Shaker has made a point that Markov is applicable only for non-negative random variables and Chebyshev for both also. Yeah, true. So that point could be right. So that's important to see. Okay, so I mean, most people have answered here. So I think many people have got it. So let me just quickly show you the solution and walk you through how I've written it down. Okay. So x is exponential 4. So if you do that, you're going to get, the expected value is 1 by 4. So probability that x is greater than 4 is 1 by 4 by 4. It's 1 by 16. It looks low enough. But if you actually
No sound, sir.
little while seem to be talking, but
some bandwidth problem.
Now it's back.
it's back. Yeah. I think, see, our network has been a bit unpredictable, so it keeps dropping and coming back. I hope you can hear me now. So you have e power minus 16 as the actual number. So no, e power minus 16. Remember, e is like some 2.7 or something. So it's 1 by 2 power 16. It's a really, really low number, some 10 power minus 7. So look at the difference. So like I said, when you know the distribution, really, really well, Markov will give you very seemingly, poor answers. Same thing with Poisson, x is greater than 12 is 4, 12, 1 by 3. Geometric, again, the same formula, expected value of x is 4. Just be careful with all these calculations. Pay attention to the formula, pay that extra bit of attention. You'll get it. But even for the geometric case, you see that, 0.5 and 0.1. So the upper bound seems really, really off. Okay. Okay, so that's the solution. Once again, the solution PDF will be shared with you. There's no need to furiously copy. You'll get this. Okay, so I think the next set of questions is probably the first set where you may not know the distribution exactly. Okay, so here is the case, and that case traditionally comes with sums of random variables. So sums of random variables is the case where the expectation is very, very easy to find, but the distribution may get harder and harder and harder, right? And sums of random variables show up all the time. Okay, so you should get a good handle of this, and you'll see Markov's inequality will be useful in this case. Okay, so give it a shot. Give this a shot. So there are 5 random variables. These are all IID uniform continuous random variables, uniform in the interval 0, 100. And then I define a new random variable x, which is the sum of these 5 IID random variables, x1 plus x2, so on till x5. Okay, so I'm adding these 5 random variables to get a new random variable x. Okay, I want you to find an upper bound on probability that x is greater than 450 using Markov's inequality. Is there any intuitive proof? Okay, so once you know Markov inequality, Chebyshev's inequality is trivial, right? right? Chebyshev's inequality is just an application of Markov's inequality to the random variable mod x minus expected value of x squared. Okay, so you take, x minus expected value of x squared, that's the positive random variable. You apply Markov to it, you get Chebyshev. So Markov is the source. Chebyshev is just a very simple derivation. For Markov inequality, there are proofs, though I didn't do it in my lectures. You should be able to find numerous proofs on Stack Exchange, on Wiki, etc. And many of them are very simple. They're very simple pictorial proofs. So the easiest way for me to see it is, if the probability that x is greater than t is bigger than expected value of x by t, then the expected value of x will not be expected value of x. Okay, so it has to be something bigger, right? Because the greater than x is greater than t, the probability of that is bigger than expected value of x divided by t. So if you just integrate that part of x, you will get something bigger than e of x, right? So that's sort of like the intuitive simple proof. Okay, so overall x has a certain average value. Its integral in one part itself is bigger than that, it means it doesn't work. So that's one. So that will work. Yeah. So I think Bimlesh has put down the proof for Chebyshev's inequality. Once you know Markov, Chebyshev is straightforward. And for Markov, there's like this simple proof involving that. Okay, so there's about 20 responses. See, remember, the expected value of x is linear, okay? So if you take expected value of x, when x is the sum of x1 plus x2 plus x5, the expected value of x will go off to the right as expected value of x1 plus expected value of x2 plus so on till expected value of x5, okay? So expected value of x1 is what? It's 50, isn't it? It's uniform, continuous between 0 and 100. We saw the formula a little while ago. It's 50. So expected value of x is going to be 50 plus 50 plus 50 plus 50 plus 50 plus 50. So it's just 550s added up together. So you know expected value of x is 250. So that's the crucial number there. Once you find expected value of x is 250, you can get a bound on this using Markov. Okay, so it will be less than or equal to 250 by 450. So the answer should be 5 by 9. Many people have got 5 by 9. 5 by 9 is not 0.11, isn't it? 0.55. Okay, 5 by 9, 0.616. How do you get 0.616? You can't get that. So most people have got 5 by 9. 5 by 9 is the correct answer. 1 by 9 is not correct. 5 by 9 is the correct answer. Okay. So remember, it's just a question of finding expected value. So once again, I want to reiterate here. In this case, can somebody say, okay, sum of uniform is not uniform? Yeah, it's absolutely not uniform. It's not uniform at all. So sum of 5 IID random variables is it's complicated to find the distribution. Okay, so you have to do some convolution type thing and all that. It's very complicated to find the distribution for x1 plus x2. You may be able to find it and you may be able to do it, but it's a lot of computation. But notice how expected value of x is so much easier to find. Okay, so once again, I want to reiterate, there will be several situations like this where expected value will be very easy to find. Even realistic situations, very realistic situations, where you will be able to estimate the expected value of something, but you will not be able to estimate the distribution of that something. Okay, so for finding the distribution, you need lots of data. With little bit of data, you can find expected value. So when you know expected value, you can get a bound for such events, and those bounds are useful, and that comes from Markov's inequality. Okay, so here's the first problem in this case. Now I want you to look at the second problem. Okay, very similar to before. Just use the fact that expected value of something is okay. So there's a small typo here. It's not x greater than 80. It is s greater than 80. Okay. This one is very similar to before. Yes, somebody is asking about linear combination method. Yes. So so expected value is like a linear operator. So if you do expected value of ax1 plus bx2 plus cx3, etc., whether or not x1 and x2 are independent or not, you can always take the expected value inside over the summation. So when you want to find here, when you want to find expected value of s here, it is straightforward. It is just expected value of x1 plus expected value of x2 plus so on till expected value of x50. Okay, and each of these expected values are the same. It's just the expected value of x. So it's a very trivial thing to find the expected value of this guy and then find the expected value of s. If you have to find the distribution of s, you have to do a lot more work. It's very, very painful, and it may not even be a very illuminating answer. Apologies for the typo here. It's not probability of x greater than 80. It is s greater than 80. Okay, I'm able to correct it. Okay, hopefully you see that there's only one little trick here. It's finding expected value of s. How do you find expected value of s? It's just 50 times expected value of x, right? And you have to find expected value of x, and x is the distribution is given to you, so it's very trivial to find expected value of x. Once you find expected value of x, just substitute it here. You will get 50 times that as expected value of s. Okay. Okay, so we give it a little bit more time. Okay, so about half the people have responded. So let's go through and see the responses. 0.28125 is perfectly right. 0.45 by 80. Is that the same as 9 by 32? I don't know. I don't want to keep dividing. Okay, 9 by 32 could be the answer. Good. Very good. So 1 by 8 is not correct. So that's this is correct. 0.45 by 80 looks about right to me. 0.45 by 80 is not correct. It's wrong. It's wrong. 0.28125 is correct. It's 50 times 0.45 by 80. The 50 times is something left out here. See, 0.45 is expected value of x, but I need expected value of s. So for that, I need to multiply by 50. Okay, so it's 50 times 0.45 by 80. Okay. So it's not 5 times 0.45, Manu. It's 50 times 0.45 by 80. Okay, okay. Okay, I guess you've done 8. So that's okay. That's correct. Okay. So that's the correct answer. So it's good. It's good that you've done that. So now let's see one more. Once again, I want to emphasize the point I wanted to make here. You could find the distribution of S, but it's a lot of work in this case. You have to really struggle a lot, and from there going to probability of S greater than 80, you need to find the distribution of so many points. And it's really painful, and it's not very useful. So if you want to get a good quick upper bound, here is an upper bound 0.28125, right? So it's very useful when you have to do Markov. Okay, so the last problem involves a beta distribution. So let me just bring up the formula for the beta for you. The beta distribution is a continuous distribution taking values in the interval 0 to 1. There's the PDF for you, but here is the important formula. Beta of alpha beta, the expected value of x is alpha divided by alpha plus beta. Okay, it's alpha divided by alpha plus beta. What looks scary? So Aniket, don't say my video looks scary. Is it that bad today? I'm a little bit tired, but PDF, okay. Okay. All right. So I mean, I don't know. See, to me, these expressions are so familiar that they're not scary. So you're afraid of what you don't know, right? So once you get to know these objects, so look at that. So ignore, first of all, you should know to ignore the constant, right? See, in any PDF, the constant is, I mean, it's sort of there, but you don't really bother so much about the constant, right? It's something that makes it one, and then you have to just look at x. X is the variable here, and you see x power something into 1 minus x power something, and that's it. It's a nice polynomial. You'll get something very simple. I mean, if alpha is an integer, alpha beta is integer, it's simple function like that. Okay, so nothing to be scared as such. But anyway, so the beta of alpha beta has a mean which is alpha by alpha plus beta. Okay, so this is the formula for the mean, alpha by alpha plus beta. So now if you come back here, if I have 100 IID beta 3 comma 10 random variables, and then I do this averaging, okay, so this is the average. This y is the average of all these 100. I'm not summing it up. What is numerator of the first sign? Okay, Bimlesh, I'll come back to your question later. But first let me describe this question. This is y is x1 plus x2. Remember, there's a division by 100. Pay attention to that. Yeah, and then you have to use these kind of properties. So when you take expected value inside, the constant will simply come out and multiply, right? So you just remember to use that very carefully, and then find the expected value of y. Once you find expected value of y, it's a textbook problem to use probability that y is greater than 0.5, right? So then once you do that, your Markov's inequality is done. Okay. Connection lost. Nobody can hear me. Is that right? Looks like I'm on. Am I on?
Audible.
Okay. Okay.
We
Thank
can
you.
hear you.
Okay. Thanks. So you have to use the formula for the beta distribution. It's alpha by alpha plus beta. So it's 3 by 13. So expected value of xi is 3 by 13. And here there is like 100 of them being added and divided by 100. Okay. So somebody commented that the beta distribution looks scary. Here are 100 of them and they're all getting added. So it's true that finding the distribution of y is a difficult exercise. It's not easy. However, you may really want to know whether y is going to be greater than 0.9. So this is what you may want to know. In that case, inequalities like Markov's inequality will really, really help you. Okay. I wanted to do Markov for a little under 1 hour and then jump into Chebyshev. So let's see. There's one more problem with Markov and then we'll jump into Chebyshev. So let's see if we can do this quickly. Just pay attention to that properties of expected value when you push it to the right side. Don't miss out that factor of 1 by 100. When is the beta distribution used? What week are you in the lecture? Are you in week 1 or week 2? No, not week 8 or week 9. I mean, it's week 10, no? Week 7. Okay. So wait for the estimators to come in. When you want to do some estimation, you'll see some beta distribution comes. So the actual situation, if you think in terms of histograms, beta distribution lies between 0 and 1, right? So if you want some distribution which will exist only between 0 and 1 and not have a flat shape, right? It has some interesting, polynomial type shapes, then the beta distribution is really, really useful. Okay, so it's a good model for that. Quite often, when you want to estimate a Bernoulli random variable P, right? The P of a Bernoulli distribution you want to estimate from data. People typically assume P to be from some beta distribution. So you will see in the estimation chapter, as you come to it, you'll see the beta distribution being used. No. I don't think beta and Poisson are related. See, beta distribution is between 0 and 1, right? Poisson is like, I mean, it goes on and on and on. 0, 1, 2, 3, infinity. It's discrete. This is continuous. No. Beta is not a generalization for Bernoulli either. It's a strange distribution. Okay, so don't. Bernoulli is like discrete, no 0, 1. Beta is continuous between 0 and 1. So it's more delicate. Okay, all right. So let's see. There are enough responses. Somebody asked a question about expected value of sample mean is equal to distribution mean. Yeah, absolutely right. You can use that here also. So you can use say that the expected value of y will be equal to the expected value of beta, which will just be 3 by 13, right? So that's important. And remember, beta, there's this alpha and beta, right? I think depending on that value of alpha and beta, the PDF of the beta distribution can vary wildly between 0 and 1. It's very, very different. I think I showed a few examples just to illustrate in my lecture. I don't know if you got the feel for it. I will urge you to go to Desmos or something and actually plot the PDF and see. And even Wiki might have a lot of plots of beta distribution. It varies wildly as alpha changes, alpha and beta changes. Okay. So anyway, so let's see the solution. 0.256 seems to be a popular one. Yeah, 0.2564, 10 by 39. That's correct. Okay. So it's quite simple. The steps are given here. Yeah, see, look at this. Expected value of x is 3 by 13. Y is also 3 by 13. Probability of y greater than 0.9. Wonderful. Steps are here. I don't even need to show the steps. I think this is all I had for question 4. So let me go through and show you the solution I prepared for question 4. Here it is. So once again, the point is when you have sum of IID or sum of any random variables, the expected value distributes over the sum very, very easily. Okay, so that's the important story here. So once you do that, all these three problems are very, very easy to deal with. And even when you have scaling, like 1 by 100 scaling, you can do these kind of calculations very, very easily. Okay, good. So let's move on. Okay, so the last problem I'm going to show you is going to be a little bit confusing. It's probably the most complicated problem we have seen in the Markov inequality case. So let's
Sir, no audio. Sir, no audio. Sir, still no audio.
Okay, can you hear me? Is it better?
Yes, sir.
Yes, sir.
Okay. Yeah, so it just tends to disconnect my audio and then I have to connect again. Okay, I think we're back on. So let me just describe this problem. Eventually, we'll get to a sum of non-IID situation here. The situation is like this. There are 10 balls. These are thrown one after another independently and uniformly into 10 bins. Okay, so each ball can go into any one bin uh, independent of the other balls and uniformly. So it gets into one bin with probability 1 by 10, second bin with probability 1 by 10, like that. Okay. Now I'm going to define a random variable x sub I. Okay, I could be 1, 2, 3, 4, like that. And xi is 1 if bin I is empty. Okay, so think about this once again. I have 10 balls. I've thrown it independently uniformly into 10 bins. Okay. And I look at one bin and then I ask the question whether bin 1 is empty or not after all the 10 balls have been thrown. Okay. So the question that is asked is, what is the probability that xi equals 1? Okay. And what is the expected value of xi? So this is the question. It's got nothing to do with Markov or anything. It is just a simple probability question. 10 balls are thrown into 10 bins, independent, uniform, random. And I want to find the probability that a particular bin is empty. The ith bin is empty. Fix I. I is fixed. Okay, I is 1, let's say. When this is confusing, just take I to be 1. Okay. What is the probability that the first bin is empty? Okay, so some other question going on here. We'll come to it later, but let's just see. It's a little bit of a tricky question. Seems difficult. Yeah, I guess it's a bit difficult, but think about it. Yeah, they could be identical. It doesn't really matter. I've told you already, it's independent and uniformly at random. Whether you're throwing them into one of 10 bins and independent uniformly at random. It doesn't matter whether the balls are identical or not or anything. I mean, everything goes independently uniformly at random. So the first ball should not get into the first ith bin, right? It can get into anything else. It cannot get into the ith bin. After that, what should happen? Second ball should also not get into the ith bin. Third ball should also not get into the ith bin. If repeatedly that happens for all the 10 balls, then the ith bin will be empty. Otherwise, ith bin will not be empty, right? So that's the thing. See, always the trick to finding is to take the ith bin is empty, break it down into smaller events, combine using and, or, etc. Right? There is nothing else in probability. Don't start thinking new for any probability question. Like take the event, ith bin is empty. Then can you write it in terms of the actual events that are happening? What's the actual operations? One ball is being thrown after the other. What should happen to the first ball? Right? It should not go into the ith bin. It should go into anything other than the ith bin. What's the probability of that? 9 by 10, isn't it? 0.9. So that's why the answer, I think, I don't know why Manu lost this. So Manu, you should not put the answer here in the chat box. Please use joinpd.com. Let people also think about it. So it's been quite some time. So that's correct. 9 by 10 power 9 is correct. But expected value of xi, right? Why is it 10 times? Where did the 10 times come from? I'm not adding anything, right? It is just only xi. Okay. So why is everybody multiplying by 10 to get expected value of xi? Right? Let's go back and think why that is true. See, xi is what? Xi is 1 if bin I is empty and 0 otherwise. That's all. Xi takes only two values, 0 and 1. So why do you multiply by 10 when you do expected value of xi? Where is the multiplication by 10? I never asked for any multiplication by 10. Okay. So that part alone is wrong. Expected value of xi is actually equal to probability that xi equals 1. There's nothing more to it. Okay. So there's no need to multiply by 10. So this multiplication by 10 is wrong. Okay. So this multiplication by 10 is wrong. It's just multiplication by 1. And that's just the same as probability that xi equals 1. Okay, so remember that. So that's the first question. Let me just go through this very quickly. It's just a slightly more advanced question. So the next one is same thing. Now I'm defining x to be x1 plus x2 plus so on till xn. Now I'm asking you what is expected value of x. Okay, so here is where you have to use the the linear combination or linearity of expectation. Expected value of x is the sum of expected value of xi plus expected value of x2 like that. So now you can do 10 times. Okay, so it will be 10 times, but I will let you think of the distribution of x. It turns out distribution of x is a big pain to compute. These xi's are identical, but they are not independent. They are dependent in some sense. So it's a bit more painful to find expected value. Okay, so let me leave it at that. It's just 10 times. Okay, so once you do that, you can use Markov's inequality to upper bound probability of x greater than 5. Okay, so you upper bounded. I think the expected value of xi will work out like 3.84 something. So if you want to use Markov's inequality, you'll get an upper bound, which is probability of x greater than 5 will be 3.84 by 5, right? So it's quite easy to find Markov inequality upper bound. So again, here is a case where finding expected value is much more easier than finding the distribution. So one can use Markov inequality directly. Okay, so let me just show you the solution real quick for those of you who want to see all this written up so that I can walk you through this course. Okay, so xi equals 1 is no ball lands in bin I. Bin I is empty. So that means ball 1 not in bin I, and ball 2 not in bin I, and so on, ball 10 not in bin I. Okay, so probability of xi equals 1 is these are all independent events. So you can just multiply these probabilities 9 by 10 into 9 by 10 into 9 by 10, 9 by 10 power 10. Okay, and expected value of xi is 1 times probability of xi equals 1 plus 0 times probability of xi equals 0. That's also 9 by 10 power 10. Okay, now when you add up all these guys, which is the number of empty bins at the end of 10 bins, 10 balls thrown into 10 bins, that is just 10 times expected value of xi. So you can expect about 3.5 bins to be empty, which means between 3 and 4 or something like that. But the xi are dependent. To think about why they are dependent, it's a little bit non-trivial to think of it that way. The distribution is complicated, but Markov bound is very easy. It's just 3.48. Okay, it's not 84, 3.48 divided by 5, it's 0.697. Okay, so there's one more case. There are many more cases like this you can imagine where you will get this correctly. Yes, just to confirm, Srinivasan, that point is exactly correct. Expected value distributing over sum does not need independence. Variance needs, yes, variance needs uncorrelated at least, right? So if it's uncorrelated, it's okay. You asked for expected value of xi. I'm looking at Samit Sen's question. I can consider x equals 1 or x equals 2. What is the meaning of that? I didn't understand that. So I could be 1 or 2 or 3 or 4, you're right. So whether you do whatever value of I is, x1 has the same distribution as x2, right? x3 also has the same distribution. It's either 1 or 0, right? And probability that it's equal to 1 is always 9 by 10 power 9. Okay. Yeah, so I think Rajiv has given an explanation for why they are dependent. It's absolutely right. So that's one thing. Okay, so this is a situation where one can use Markov inequality. Okay, so we're now going to move on to Chebyshev. It's about 1 hour into the session, so it's a good time to jump into Chebyshev. So once again, we're doing Chebyshev. We're going to do very simple calculation with Chebyshev, but you will need here a formula for the continuous distribution. So here is continuous uniform distribution. You need mean and variance, right? Remember, for Chebyshev, you need to use mean and variance. And here is the formula for uniform between a comma b. The mean is a plus b by 2, and the variance is b minus a whole squared by 12. Okay, so that's the formula for the variance. If you have a continuous distribution between a and b, the mean is just a plus b by 2. The variance is b minus a whole squared by 12. Okay, remember this formula. So now let's come back. Hopefully you saw the form, saw this. I'm going to change to the question. The question just shows x is a continuous random variable uniformly distributed in minus 10 comma 10. Okay. Find an upper bound on probability that absolute value of x is greater than 8 using Chebyshev's inequality. Remember Chebyshev's inequality? It says probability that absolute value of x minus expected value of x is greater than, let's say, some t is less than or equal to variance of x divided by t squared. Okay, remember the t squared, don't forget. That's important. Absolute value of x minus e of x is greater than t is less than or equal to variance of x divided by t squares. Okay, so let's use that. Okay, so there's a question about probability of going and not going. Okay, so this is not the case, right? So there are 10 bins. The ball goes definitely into one of the bins. The probability that it goes into one particular bin is 1 by 10. It's not 0.5. Okay, so it won't go into that one particular bin with probability 9 by 10. Okay, remember I'm focusing on one particular bin, the ith bin. Okay, I could be, say, the first bin. So what's the probability that no ball will go into the first bin? Okay, so let's come, think about this later. If you want, you can ask later on. Let me come back to it later. Let's proceed to Chebyshev. We moved on to Chebyshev. Okay, so here is a continuous distribution. I showed you the formula for mean and variance. You need to find the mean, you need to find the variance, then plug it into Chebyshev, we'll get the answer here. Also, calculate the actual probability. Don't forget to do that. Okay, so I see about 13 responses. The first step is to find expected value of x. In this case, expected value of x is 0. Okay, and then you have mod x minus expected value of x. So that goes off to 0. So you just have mod x greater than 8. So your t is 8. So it's greater than or equal to t, less than or equal to variance of x divided by 8 square, right? So the only non-trivial part is to find the variance of x. For variance of x, you had a formula b minus a whole squared by 12. Okay, b is 10, a is minus 10. So remember, pay attention when you do b minus a, it will be 10 minus minus 10. Let me wait for a few more minutes. Okay, so I think there are sort of enough responses here. So let me just see this. Okay, 25 by 48 is correct. So mean is 0, variance is 100 by 3. So it's very, very clean solution here. Probability that mod x minus 0 greater than 8 is okay. So it's done a little bit more confusion. Basically, I would just write is less than or equal to. So it's not equal to, okay? So I think whoever wrote the solution, it is not equal to, it's less than or equal to. Be very, very careful. It's only an upper bound. It's not equal. So it's 0.5208 is the upper bound. Actual value is 0.2. Okay. All right. That looks correct to me. I think many people would have probably got it. 52.2. So it looks like it. 25 by 48. Okay. So check that out. If you're getting this, then you have not squared the 8, I think. Be careful about that. Okay. 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 So this is the first one. Easy enough one. So we're going to change it a little bit. X is a discrete random variable, uniformly distributed. It's discrete 1, 2, 3, 100. Okay. And I want a lower bound on x equals 50 or 51. This is actually a very silly problem to do using Chebyshev's inequality, but I just wanted to put it out there for you to see how really silly answer can also come if you don't pay too much attention. Okay, so you will get a very silly answer. The actual value is very, very easy here. But here, if you want to find the variance, there is a formula for the variance. I think one of the reasons why you should see this is the discrete distribution formula for variance. Okay, so if you have a discrete uniform distribution between a and b, a comma a plus 1 comma so on till b, the expected value is a plus b by 2. Okay, notice the similarity or difference between the continuous and the discrete distribution. The discrete distribution is very, very different from the continuous distribution. This is just a set of discrete values. A plus b by 2 here. The variance is n squared minus 1 by 12. Okay. Okay. N squared minus 1 by 12. And what is n? N is b minus a plus 1. Okay. N is b minus a plus 1. So you can see it's sort of closely related to that. So Srinivasan has asked a question about actual values 0.1. So I will address it. I'll come to the actual value in a little while. After we are done with this, I'll come to the actual value. You can calculate. There's also a little trick here. I've asked for a lower bound on x equals 50 or 51. Okay. So usually we think of Chebyshev as giving you an upper bound. How will you get a lower bound? Something you can think of. Yeah, so there was a mistake in the previous one where somebody said 0.1. So if you look at minus 10 comma 10, it's 1 by 20, right? And it's between mod x greater than 8. So it could be 8 to 10 or minus 10 to minus 8. Okay, so watch out for that. If you take care of both of those, you will get 0.2. Okay. So work this out. This is a little bit tricky. I'll give you a little bit more time. I'll be back. Okay. Okay, so there's a hint from somebody. It says lower bound is 1 minus upper bound. All right, so let me see. There's only 5 responses. People are really confused about how to get lower bound. Okay. Okay. So the trick to lower bound is, see, remember probability that mod x minus t is great, x minus expected value of x is greater than something is what? It's equal to 1 minus probability that mod x minus e of x is less than that same thing, right? Okay, so that's the trick. So you can get a lower bound for probability for mod x minus something is less than x minus e of x is less than t. That you can get a lower bound for. Okay, so that's the trick to do here. Let me see the responses. Yeah, I guess people are sort of lost with this question. It's a little bit tricky, I guess, if you haven't seen it before. So maybe I should just show you the solution here. Let me just show you the solution. Okay. So the first part, let's first do the first question. It's continuous uniformly distributed between minus 10 and 10. And you have to find an upper bound of mod on mod probability that mod x is greater than 8. Okay. Expected value of x is 0. Variance of x is 100 by 3. So just a textbook Chebyshev problem. The upper bound is variance of x by 8 squared. Okay, you get 0.52. Notice how do you get a lower bound here? Okay, so x is discrete random variable distributed from 1 to 100. So expected value of x is 1 plus 100 by 2. That's 50.5. And variance of x will turn out to be 100 square minus 1 by 12. Okay, so that's okay. So these two we have found. So notice this. X is equal to 50 or 51 is the same as absolute value. Remember, expected value of x is 50.5. Okay, so I've drawn a little picture here. I don't know if you can see this picture. Please zoom in and see it. 50.5 is the expected value. 50 is on one side, 51 is on the other side. The distance between these two is 0.5. Okay, so x is equal to 50 or 51 is the same as the event absolute value of x minus expected value of x is less than or equal to 0.5. Okay, is that fine? Okay. So now what does Chebyshev tell me? Okay. So let me see if I can zoom here. Just hold on 1 minute. The zoom work. Okay. Okay. Maybe you can see the picture a little bit better here. Okay. So 50.5 is the expected value of X. Okay. I want 50 or 51, and you can see 50 and 51 are within 0.5 of 50.5. Okay, 0.5 to left side, 0.5 to right side. So the crucial thing to understand here is X equals 50 or 51 is the same as mod X minus E of X is less than or equal to 0.5. Okay, so that seems fine enough. So now what is the point here? How is upper bound and lower bound related? So what will happen here is this probability that mod X minus E of X is less than or equal to 0.5 equals 1 minus probability that mod X minus E of X is greater than 0.5. Is that okay? Hopefully you saw that. This is the trick. Okay. So you can write it, you can rewrite it the other way around if you like. So if you get an upper bound for this expression, you will get a lower bound for this other expression. So how to get a lower bound for this? You just get a upper bound for this other expression. Okay. So maybe I'll zoom a little bit lesser. Okay. So this is maybe a little bit better to read now because anyway you're reading. So I need an upper bound on this guy, right? So probability that X minus E of X is greater than 0.5. This is less than or equal to variance of X by 0.5 square. It turns out this upper bound is very, very large. Okay. So this is a ridiculous sort of upper bound. But if you get an upper bound on this, you will get here an upper bound, lower bound, which is this way. Okay. So let me just write it out fully for you. So it turns out this will be greater than or equal to 1 minus variance of X by 0.5 square. Okay, so this is the actual way to get the lower bound. Okay, think about how I got that. So this guy is less than or equal to variance of X by 0.5 squared. So 1 minus that guy is greater than or equal to 1 minus variance of X by 0.5 squared. So the lower bound that I want is actually 1 minus variance of X by 0.5 square. So it turns out variance of X by 0.5 square is very large. So you will get the ridiculous upper bound of greater than or equal to 0. Okay, so that's what you will get. But anyway, so it's not so interesting for us. But this is how you get lower bound on probabilities using Chebyshev inequality. So this is an important thing. You can also get a lower bound on probabilities using Chebyshev inequality, but it needs to be of the form mod X minus E of X less than or equal to something. If you rewrite the probability as mod X minus E of X is less than or equal to something, then you will get a lower bound on the probability. Okay. So here we get a trivial bound. You just get the values to be greater than or equal to something negative, which means it's greater than or equal to 0, right? So it's a very trivial bound, but in reality you may get better bounds. I think I should have asked for a slightly better thing than just 50 or 51. I should have asked for X going from 25 to 75 or something. In that case, you would have got a slightly better value. Okay. Okay, so see, remember the bound given by the right-hand side expression here is not a probability. Okay, the bound on the expression on the left-hand side is a probability. Everybody is asking how can probability be greater than 1? It's not greater than 1. Okay, so the quantity on the left-hand side is a probability. The quantity on the right-hand side is a bound on a probability. It can be something greater than 1, which means what? It becomes a trivial bound. It's a stupid bound. Okay. So if I want to compute a probability, the easiest upper bound I can say is 1, right? That value of a probability is less than or equal to 1. I can also say 2, or I can also say 20. Probability is less than or equal to 20. It's definitely true, right? It's an inequality. It's a trivially true inequality. In this case, for this particular expression, you're getting a trivial inequality. It's a bad inequality. Okay, so it's useless inequality. So don't worry too much about this particular value. But the right hand side in the Chebyshev inequality need not be a probability. It need not be a valid. It need not be less than 1. It can be greater than 1. Okay, so this example hopefully illustrates that to you. So you can get something like this also. So watch out for that. So Chebyshev and Markov can give you very silly bounds sometimes. Okay, keep that in mind. Okay, so let's move on. Coming to the last end of our session here. So let's move on and see some textbook problems which are very, very easy to do. So here is the next one. Okay. It's a binomial problem. So you have a fair coin that is tossed 200 times and you have to find an upper bound for the probability that more than 150 or fewer than 50 will be seen. So you can draw that picture that I drew, right? So you find expected value of x. Oh, okay. By the way, I forgot to show you the variance formula. Sorry about that. So let me show you the formula for variance. So you can have the binomial distribution of n comma p. The mean is np. Variance is np times 1 minus p. Okay, so that's the variance. Variance is np times 1 minus p. The mean is np. Variance is np times 1 minus p. Okay, and then draw that picture, that little picture that I drew in the previous case, right? I had expected value of x in the middle, and then I was looking for what's there on that side, what's there on this side, and then convert that event into absolute value of x minus expected value of x is greater than something. Once you do that, you can use the textbook Chebyshev formula. That's it. So it's NP and NP times 1 minus P is the variance. Okay, see a few responses slowly trickling in. Okay, so I see about 15 responses. Maybe I'll wait for a few more minutes for people to figure it out. Okay. Okay, so I think it's come close to 20. So the answer that many people have given is 1 by 50. That's correct. 1 by 50 or 0.02. Okay, so whoever has found out 0.02 or 0.98. What is 0.98? Okay, so it's 0.02, I think. So it's good. Okay, all right. So okay, so I think the person was not sure whether it's this way or the other. So 1 by 50 is correct. So we'll do part B and then I'll show you the solution to both. That might be interesting. So here is part B. Again, a binomial but biased coin. Head is 1 by 3 probability. You have to find the probability that more than 150 heads are seen. Okay, that's the event here. It just takes practice to figure out what that mod x minus e of x has to be. What is e of x? What is variance? And what is that difference term? So here I've only given more than 150, right? I'm ignoring less than 50. So what about that? Is that okay? Can I also ignore that? All those things you just think about for a little while, and you'll get to it quickly.
मौज हो गया तो क्या बोले नंबर मैं रेजिंग हो रहा है
Okay, somebody has their mic on.
पता ना
Talking to somebody else. Manish Kumar, you should mute your mic. Okay, so once again, the probability that the first step is x is the number of heads that you see, right? So it's binomially distributed with n equals 200 and p equals 1 by 3. So what's expected value of x? It will be 200 into 1 by 3. What is variance of x? It's 200 into 1 by 3 into 2 by 3. Okay, so all these three are easy steps to write, straightforward steps. Now, you want to find an upper bound for the probability that more than 150 heads are seen. Okay, so the event is what? X is greater than 150. Okay, so it's x is greater than 150, right? So expected value of x is 200 by 3. 200 by 3 is somewhere, and then you want to look at 150. So what is this gap between 150 and 200 by 3? It's 150 minus 200 by 3, right? So what is the distance between 200 by 3 and 150? It will work out to something. Okay. So now, so you have to work like that. Work your way slowly through that. Okay, work your way slowly like that. So you want x is greater than 150. You write that as mod x minus 200 by 3 is greater than what? That's what's important. So x is greater than 150. Probability of x greater than 150 will be less than or equal to probability that absolute value of x minus 200 by 3 is greater than something. I think that is 250 by 3 or something like that. then you use Chebyshev. Okay. So remember that it's also possible that you will have a less than 50. I don't know how to mute all the participants. I hope if I don't know if I'll even have the rights to mute all participants. Do I have the right to mute all participants? Maybe Karthik, if you're there, I don't know if he's there. He should be muting all the participants. Okay, there's about 11 answers. I don't know if there are going to be more answers than that. So yeah, so this 4 by 625 looks sort of correct. This 4 by 625 is correct. There's also some 8 by 625. I think the minor term has missed. 4 by 625 is correct. So somebody is trying to write it down. 4 by 625 is correct. You have to slowly work it out. It's 0.0064, I think. That's the correct answer. It's a very small value. 4 by 625. 400 by 250 squared. Yeah, that's also correct. 400 by 250 squared is correct. So some people have figured it out. So let me show you the answer to both the A part and the B part. Okay. We'll just work through the answer. Okay. So this is 6. So let's go to 7. All right. So A part is a fair coin is tossed 200 times. Okay. And find an upper bound of probability that more than 150 or fewer than 50 heads are seen. Okay. So first thing is identify the random variable. Okay. What is the random variable head? Here is number of heads when the fair coin is tossed 200 times. So that is binomial with n equals 200 and p equals half. And from there you find expected value of x, which is 100, and variance of x, which is 50. Okay, 200. Now comes the next step, which is translating the event that is being asked into the form that you need for Chebyshev. Okay, so this is a little bit of a trick. It's not very hard, but you have to just look at it and carefully do it. Okay, I've asked for x greater than 150 or x less than 50. So always draw this. I like drawing this little picture here. Maybe I should zoom a little bit. People are talking about the zoom being an issue here. So let me just zoom a little bit. Hopefully you can see that. Okay, so 100 is my mean. I'm going less than 50 or greater than 150. So you draw that like this on a number line, and then look at the distance between 150 and 100. 50 and 100. You see 50 shows up as the distance on both cases. So you can easily see and easily argue this out that x is greater than 150 or x is less than 50 is the same event as absolute value of x minus 100 greater than 50. Okay, so this is a little trick here. Once you identify this, Chebyshev inequality is direct. Okay, probability of x minus 100 greater than 50 is less than or equal to variance of x. 50 is the variance of x. That's where it comes from. And then divided by 50 squared. So it's 1 by 50, 0.02. So compare with the Markov inequality bound. We did the same problem in Markov, right? You got 2 by 3 in Markov. Okay, so look at how big the Markov number is and look at how small the Chebyshev inequality number became. Okay, so Chebyshev has really worked much better than Markov. In fact, the actual probability is much, much smaller than this, but still, you know, at least Chebyshev is a little bit better than Markov. Okay, so let's go on to the next one. The next question, let me go back to the original Zoom here. Okay, so the next part B of this question is a biased coin. The probability of heads equals 1 by 3 is tossed 200 times. Once again, identify the random variable. First step is number of heads. That's binomial. Will the Chebyshev equations be given in the exam? Oh my God. Okay, so we are planning to give some formulae. I don't know if the Chebyshev formula will be given. This is binomial 200, 1 by 3. So expected value of x is 200 by 3. Variance is 200 into 1 by 3 into 2 by 3. It's 400 by 9. Okay. Now again, draw this little picture here. Again, let's just go see if the picture can be zoomed up a little bit. On 1 minute. Okay, so here's the picture zoomed up. So my expected value is 200 by 3 and x is greater than 150 is what I'm looking at. So this 150 is here and this distance 150 to 200 by 3 is 150 minus 200 by 3. That's just 250 by 3. Okay. So from here, I'll write this little thing here. So x is greater than 150 is less than or equal to probability that absolute value of x minus 200 by 3 is greater than 250 by 3. Why did I not write equal to here? Why did I say less than or equal to here? Can anybody answer that on the chat? Yeah, see, I'm taking only one side. X greater than 150 is only one side. That is a smaller event than this mod x minus 200 by 3 greater than 250 by 3, which has both sides. Okay. So I don't even care what the other side is. Other side is some 50 by 3 or something, right? So it's on the other side. So I'm taking only one side. So this will be a less than or equal to. Once I have this form, why is this form very, very nice for me? This is the Chebyshev form. I can use my Chebyshev form formula, right? So it's less than or equal to variance of x divided by 250 by 3 whole squared. And that's just a simple calculation. You can do 4 by 625.0064. Now compare this to Markov, which gave you 4 by 9, right? You did the same question in Markov. You got 4 by 9. Look at how much better the Chebyshev inequality is, 0.0064. Okay. All right. So let's go back to the next question. So this is all just textbook problems. So it just involves different distributions. I just wanted to give a very simple problem just to get started. X is normal 0, 2. So what is the expected value of x? Expected value of x is 0. Variance of x is 2. Okay. When I say normal 0, 2, expected value of x is 0. Variance of x is 2. Okay. Find an upper bound on probability of absolute value of x greater than 8 using Chebyshev inequality. It's a very, very easy, straightforward application of the formula. Okay, there's nothing more going on here. So how to understand 3 sigma rule? Okay, so in this kind of case, so for instance, this is sort of like the, I don't know, it's not so. So it's in the normal case, the 3 sigma rule or 4 sigma rule or 6 sigma rule or whatever you want to call it. So if you say absolute value of x minus e of x is greater than say 6 times sigma, right? It's going to be less than or equal to sigma squared divided by 36 sigma squared, right? So it's going to be 1 by 36, right? So it's just an upper bound on the formula. So if you say 3 sigma, it's going to be 1 by 9. So 1 by 9 is roughly like, 10% or something like that. So 10% of the people are beyond 3 sigma, right? 3% of the people are beyond 6 sigma or something like that. So that's the approximate. I mean, just normal distribution. You blindly use Chebyshev, you'll get it. Okay? In fact, you can get much better approximations than that for normal, but in reality, it may not be normal. Yeah, so sort of outliers. Yeah, true. You can think of it as outliers. See, x is normally distributed, mean is 0, variance is 2. You sort of expect x to be around 0, right? Maybe 2 minus 2. Absolute value of x greater than 8 is outliers on either side. It's either greater than 8 or less than minus 8. Okay, very two-way outliers. And you can do Chebyshev inequality to get some formula. Okay, so 15, 16 people have responded. So let's go in and see the responses. Yeah, 2 by 64 is sort of straightforward answer, right? It's just a direct substitution of the formula. 1 by 32.03. Okay, good. I see correct answers here. Let's go on to the next one. I think very simple. I've not confused people here too much. I've just given straightforward form suitable for Chebyshev, just for people to get a little bit more comfortable. Okay, normal 100, 10. Find an upper bound on probability of mod x minus 100 greater than 80. A straightforward application of Chebyshev. You can call it the it's one of the probably the simplest problems. I don't know. Maybe I should have complicated this a little bit more, but all right. We'll see. Okay, so I don't want to wait too long for this. I think people would have gotten this. Yeah, so it's 10 by 6,400. 0.8 is not correct. 1 by 640 is correct. So this is the correct thing. So yeah, so expected value of x is 100, variance is 10. This is just straightforward. 10 by 80 squared, variance of x divided by square of this. Okay, so I think I may have the solutions written up just because I wrote it up. I'll show it to you. It's straightforward here. Yeah, I've just written a couple of quick application of the formula. You can see here variance is known. X minus x is 2 by 8 square, 1 by 32, 10 by 80 squared, 1 by 640. Okay, so let's go on to the next one. I think next 2, 3 are a little bit more involved. Okay, maybe not. Okay, so this is exponential distribution, the same thing as before. Maybe I should skip this. So the next 3 are textbook applications. So let's do this alone. We'll do this alone. You may want to see the formula for exponential distribution. For the exponential distribution, this is the continuous distribution here. The expected value is 1 by lambda. Variance is 1 by lambda squared. Okay, so this is mean and variance for the exponential distribution, 1 by lambda and 1 by lambda squared. Is that okay? So this is mean and variance. And now you're ready to use Chebyshev. It's a little bit tricky. Pay attention to the expected value and be careful when you say probability x greater than 4, you have to translate it into something suitable. Okay, so be careful about that. So you have the mod x minus expected value of x. Okay, so expected value of x is not 0 here, so just pay attention to that. You will get the correct answer. Okay, so we're coming quickly up on time. So let's just go through and see. Okay, many people have not. Wow. Okay, 1 by 225. My goodness. Let's see. Okay, I didn't quite see the correct answer, I think. Or at least the answer I have. Okay, something is going on here. I think 1 by 15 squared. Why do you get the square here? Okay, it's good. Okay, I think that's correct. Slowly getting to the. Okay, that should be good. I think 1 by 15 squared is correct. 1 by 256 is not quite correct. 1 by 640 is not correct. 1 by 225 is correct. 1 by 15 squared is correct. So 1 by 15 squared is correct. Yeah, 1 by 225 is Chebyshev. 1 by 16 is Markov. That's good to see. Okay, so enough people have got the correct answer. Now, there is similar question with Poisson and geometric also. Okay, so I'm not going to discuss all these things or give you enough time for all these things. So let's go through and see the solution again. Something I've written up. Okay, so I've written up the solution here. So the trick is to be very careful about this event that I'm asking. Okay, so exponential 4, expected value of x is 1 by 4, variance is 1 by 16. Okay, I'm asking for x greater than 4. Now I have to go to this mod x minus 1 by 4, right? So I have to say x minus 1 by 4 is greater than 4 minus 1 by 4 and say it's less than or equal to absolute value of x minus 1 by 4 greater than 4. In this case, I've put equal to here because the other side doesn't exist. Okay, the other side will go off negative and that is 0 and exponential. So I can put equal to here, but usually it will be less than or equal to. Look at this next example here. X is Poisson. Poisson actually expected value and variance are both lambda. Okay, 4 and 4, and find an upper bound on probability that x is greater than 12. Okay, you get that here. So you'll see, again, you have to write mod x minus 4 is greater than 8. Okay, so you do x minus 4, you get greater than 8. It's less than or equal to 4 by, which is variance by 8 squared, you get 1 by 16. So Markov was not too bad. The geometric one, 1 by 4, probability that x greater than 8. Remember, Markov gave you 0.4. It looks like if you do this, it seems like you're getting 0.75. Okay, so because of the way the variance and the difference is working, Chebyshev is giving you worse off answers. Okay, so the point I wanted to make with these things is you may get a worse off answer with Chebyshev also. It can happen in some extreme situations, but typically in most of the cases, Chebyshev will give you better answers than Markov. Okay, keep that in mind. Can we not divide the end result by 2? No. You don't even know if it's symmetric, right? So if it is symmetric about the mean, then you can do. Yeah, you're right. You should know if it is symmetric about the mean. If it is not symmetric about the mean, you cannot do that. Okay, so let's move on to the more interesting problems. Here are the more interesting problems, which is where the power of these inequalities are clearly seen. Okay, so the first example is it's a 5 IID uniform 0-100 distributions, and x is x1 plus x2 plus x5. Okay, so remember once again, these are IID. So expected value of x will go through as a summation, and because they are independent, variance will also have a simple summation. Yes, a summation, so variance will also add. Okay. So let me give you a couple of moments to finish this up. So if you're looking for mean and variance of continuous uniform distribution, here is the formula. A plus b by 2 is mean, b minus a whole squared by 12 is the variance. Okay. Yeah, sure.
I need to clear one concept that Chebyshev inequality formula you told about is sigma square over n delta square. And whatever you have shown is you have not divided by n. Why is that?
No, there's no n or anything. Okay. See, if you apply Chebyshev inequality to the sample mean, you will get that soon enough in some other example. The sample mean is 1 by n, x1 plus x2 plus so on till xn. Okay. So if you have that 1 by n there, some n and all will come. Okay. And here I'm not doing that, right? It's just the sum, x1 plus x2 plus xn, x5. So Chebyshev inequality is probability that absolute value of x minus e of x greater than t is less than or equal to variance of x divided by t squared. That's the formula. Okay. Is that all right? Sometimes I would have written maybe t as, some k times sigma. If you write t as k times sigma, you will get variance of x divided by k squared sigma squared. And then the sigma square is what? Is variance, right? So it will cancel. So you will get 1 by k squared. Maybe I wrote like that. I don't know. Sometimes you can write the t to be k times sigma. And then you will get just 1 by k squared. Or another way to write it is greater than t. It's less than or equal to variance of t by variance of x divided by t squared. Okay. So in this case, next time when I apply it in the solutions, I'll show you. Okay. So let's see the responses. Okay, so let's see the responses. About 15 people have responded. 1 by 48. Okay, seems to be 5 by 48. Okay, so I think 5 by 48 is what I got as well. It looks correct enough to me. Okay, so check your answer. 5 by 48 is what you should be getting. 1 by 48. 1 by 48 seems to be a very popular answer. Why is that? Why is 1 by 48? Okay, I think you get 1 by 48 if you don't multiply by 5. Okay, remember, see, the variance of x is actually not equal to variance of x1. You have to add 5 times. So it's 5 times the variance of this distribution. It's not just one of them, right? You've added up 5 times. Not just the mean, the variance will also add. Okay. So intuitively, just think of why is it that variance should add when you add it up. See, each random variable has its own variations, and you're adding 5 of them. So clearly, the variances must add, and they're all independent. So you cannot have the same variance for x and x1. Okay, keep that in mind. Okay. Yeah. So if you divide by n, it's not the same variance. If you divide by n, the variance will be by n. Okay. If you divide by root n, the variance becomes the same. Okay. Anyway. So pay attention to that. That's important. Okay, so that's the 5 by 48 is the correct answer here. There's a similar question, similar to before. This is the discrete distribution that we have, and 50 of these random variables independent are being added. You have to once again find the mean and the variance of this distribution. It's a little bit of calculation, so I'm not going to ask you to do it. Let's just jump to the next one, which is the beta distribution. Again, there is a little bit of calculation involved. You have to know the variance of this distribution. So to just cut short and in the interest of time, let's go ahead and see the solution. And I'll quickly walk you through the solution of all three, and we can just look at the answers. Okay, so for the first one, expected value of xi is 50, variance of xi is 100 minus 0 squared by 12. Expected value of x is 5 times expected value of xi is 250. Variance of x is also 5 times variance of xi, which is 5 times 10 power 4 by 12. So if you look at mod x minus 250 greater than 200, it's a textbook case of variance of x divided by t squared. Okay, so variance of x divided by t squared. It's a very easy formula to remember. So we'll get 5 by 48 as the answer. Okay, so for the next one, discrete given the same distribution we used for the Markov also, probability of x greater than 80. Now we need to find expected value of xy and also variance of xi. Given this distribution, you have to find the variance. It will come out to 1.6125. I'm not showing you the calculation. It will come out to something like this. So expected value of x is 50 times this, 22.5. Variance of x is again 50 times this, 1.625, which is 80.625. Okay. Yeah, the formula PDF will definitely be shared with you. It will be put on the portal. Don't worry. Probability x is greater than 80 is probability that x minus 22.5 is greater than 80 minus 22.5, which is equal to 57.5, which will be less than or equal to probability that absolute value of x minus 22.5 is greater than 57.5. And then you use your Chebyshev formula, you get 0.024. The corresponding Markov was 0.28. Okay, so this is an example. Beta distribution is a little bit more involved. There's a formula for the variance. I'm not giving it here. You can write it down. And then after that, it's just the same method, except that there's this 1 by 100. So notice what happens to variance when you do 1 by 100. It's going to go 100 times 1 by 100 square times the variance of the beta. So you will get a further 1 by 100 in the denominator when you divide. Okay, remember the variance, see, so variance of Cx is C squared times variance of x. Okay, expected value of Cx, Markov had written that formula a long time back. Expected value of Cx is C times expected value of x. Variance of Cx is C squared times variance of x. So that's something to remember. Multiplication by constant, you'll get the square of that when you do variance. Okay, so you do 100 times 1 by 100 squared. So 100 might cancel here. So you'll get a slightly different formula. So you get 0.00028. Okay, so I don't have the Markov value is 0.2564. So notice how much smaller the Chebyshev inequality is. Okay, so Chebyshev, when you can find the variance, Chebyshev gives you, thanks Manu. So I think he listened to my complaint of him not having, so he's right and up. That's good. So When you know the variance, look at how much better the Chebyshev inequality is in giving you the upper bound on this beta distribution. Okay, so there's only like a couple of minutes left. We don't have too much time, but I'm going to still leave you with the most difficult challenge question of the day, right? We come up to the last one. I put a star there saying that it's really a challenge question. I'll give you the same question, 10 balls thrown into 10 bins. Okay, I want you to think of x, which is x1 plus so on till x10, which is the number of empty bins. Same question as before. Okay, sum of non-IID. Now you have to think of x squared. Okay, so why am I thinking of x squared and finding expected value of x squared? Because I want to find the variance of x. Okay, so I want to go through and find the variance of x. Okay, so that's why I'm asking you to think of this. Okay, so I don't have the solutions written up. I'm not going to show you the solutions. This problem will be put up later on the website. You can go take a look at it. It's a little bit of a challenge problem. It's not very trivial or easy. It's a little bit more involved. You have to first write x squared. After you write x squared, you can try to do expected value of xi squared. Okay, for every xi is 1 or 0. What is the expected value of xi squared? Okay, this is actually very easy to find. What is slightly more tricky to find is expressions like this. What is expected value of x1, x2? Expected value of xi, xj. Think about what xi times xj means. Xi times xj is 1 when. So think of that. You can find this. Okay. Like I said, I'm not going to solve it here for you. I'm not going to show you the solution. I'll leave it in the portal. You can attempt it when you have time. It's a little bit of a challenge question. Okay. So once you find expected value of xi squared, expected value of xi, xj, you can actually write down a very nice expression for expected value of x squared. Okay. So it's possible. Think of why that is true. If you do x squared, you will get a lot of terms here. They will either be of the form xi squared or they'll be of the form xi, xj, and they will all be adding up. So you can just push it inside. No, Shaker, don't go so fast. It's not independent. Expected value of x1, x2 is equal to the product of expectations only when they are independent. In this case, they are not independent. Okay, these xi's are not independent, so you just can't push the expected value inside. Okay, so you have to actually do the calculation more involved way. You'll find variance of x. Once you find variance of x, you can find probability of x greater than by using Chebyshev inequality. So Chebyshev inequality. So why did I give this last problem? Just to tell you that using Markov inequality can be in many cases much simpler than using Chebyshev inequality. Chebyshev inequality needs the variance. Finding the variance is a bit more complicated. You need to find these correlation coefficients, this, that. It's not so easy. Okay, so on the other hand, mean is really easy, and that's a true statement. Okay, so anyway, this problem will be put up. Those of you who are interested in solving it, go ahead, take your time, solve it. You can post it on Discourse and we can have a discussion around it. Okay. Once again, thank you very much. I think that brings us to the conclusion of this problem session we wanted to have. I've discussed Markov and Chebyshev in some great detail. I've also given you a bit of a challenge question. Take it with you, try to solve it. The next session we have, I'll schedule it sometime. We'll discuss continuous random variables, the contents of week 5 in particular, some calculations around continuous random variables. Thanks again. Okay, thanks to all of you for participating as well. It was, I hope it was useful to you. Several problems of this nature are good to do. Have a good night. I'll catch up with you again during the next session. Thank you very much.